Hello everybody and welcome to another video, and this is the second video of the problems and solutions chapter. I promised you last video we saw the problem of underfitting and overfitting for both linear and logistic regression, and I promised you that in this video we're gonna see the solution for these problems. So let's go straight forward for that. So what we're gonna see here is a term called regularization, which is the solution for the problem of especially overfitting. And in this video, we're gonna see the solution for linear regression, for both linear regression and logistic regression. So let's get started. I'm gonna be straightforward in that. Actually, the regularization term is something we add to the cost function. So it's something we add to the cost function to prevent it from overfitting. So let me show you how. This is the hypothesis function that like fits perfectly our data, and we said that if we make more complex hypothesis function, as like you see here, until x to the power of 4, so it's super complex, we're gonna have a great fit for the training data, but really bad for generalization to new examples, new data. So the idea is to keep the parameters as low as possible, as close to zero as possible. Like as close to zero as possible. Actually, as low as possible is wrong term, because you can imagine, oh, as low as possible, let's make it like minus 2000, like that, which is also bad. We want it like as close to zero as possible. Doesn't care about the it's minus or positive, like positive or negative number. So we add these parameters. For example, we know that the quadratic function is the perfect fit for our data. And so what we want to do is to minimize like this and this, W1 and W2, because they are multiplied by the x cube and the x to the power of 4. So that means if we like keep these close to zero, that means all these terms are going to be almost equal to zero. We can even like delete them. Not really delete them, but like they are so small, so close to zero, that they don't really affect the hypothesis function. So the hypothesis function gonna be quadratic by definition, almost quadratic, let's say. So that's a great idea. But you're gonna ask why we added specifically to the cost function that we studied already. This is the mean square cost function, because we are talking about linear regression, of course. Putting that in mind. So you're gonna say why we added to the cost function. You know that our goal from the cost function is to minimize it. We're gonna minimize the cost function. So if W1 and W2 are high, we are not going like to have like really minimized cost function. So while we are executing the gradient descent algorithm, the cost function is going to be as low as possible. So it's gonna take with it W1 and W2 squared here. So that's why we add to the cost function. It's just because the easiest way to learn W1 and W2 as low as possible. Let me see if... Okay, so small values for the parameters to have simpler hypothesis function. Yeah, actually, this is called also the simpler hypothesis function, because we are getting rid of this term. Let me make it... So we are getting rid of this term and this term, so we're gonna have only the quadratic function, and it's simpler than all of this function. And in that way, our hypothesis function gonna be less prone to overfitting. although we add like uh, bigger terms. So, but the problem usually we have too many features. There is a problem. Like here, as I showed you in that example, we have just like 1, 2, 3, 4, or maybe even this is just one feature like X. So it's you're gonna think, okay, it's just like one feature. Actually, here it's just one feature because we are talking about given the size, predicting the price of the house. So it's just one feature, no problem. And like you can, like as we did here, we're gonna say, oh, okay, the W1 and W2 are the ones that are causing overfitting. So we can just like add them to a cost function, and that's all. But the problem is, mostly in machine learning problems, we're gonna have like 100 features, all of them like with different parameters and even more than 100. So how we can do that manually, like this manipulation, this adding of W1 and W2 manually is not going to work for all examples. Generally is not going to work in machine learning. So how do we do that? So how we can decide which parameter wi to add in the regularization term? Simply, we don't do that. We just try to make all the parameters small by adding them all. That means this is what's called the regularization term here. Lambda multiplied by the sum of uh, of all the parameters square. So by doing that, we are making all the parameters close to zero. At the same, that means, what does that mean? Like the intuition behind that. The intuition behind that is every single feature of our features, like 100 features or more, doesn't matter. Every single feature is gonna contribute by like a small amount of momentum, if you can imagine it like that, like a momentum uh, to drive our function, like the hypothesis function, to not overfit. At the same time, we can use like a, a higher polynomial or any kind of hypothesis function without overfitting. So this is the idea of regularization. We add this term. This is the term of regularization. We add it to the cost function so we can minimize the parameters as well with the cost function itself. So the regularization for linear regression, we saw it already. Uh, we said we add the regularization term to the cost function. Now, uh, as you like might pop up in your head that adding this term here, that means we're gonna have to change the gradient descent, because the gradient descent is dependent on the derivative of the cost function. So the change that we're going to do on the gradient descent is adding this term. How we got this? Just simply by derivating this term here. And here in this gradient descent, I just put the the bias, aside, because usually I was, as we saw in previous videos, I was putting the B, like considering the B with the W, and we call it in the early videos W0. But now I decided to take it away because, of course, we are not going to put a regularization term with the bias. So the regularization term come with the parameters W. So it's here W for J from 0 to N is the number of features, M here is the number of examples, is the same exact gradient descent we saw before. We just added this term. This is the only difference. So this is regularized linear regression. And now for logistic regression, how to solve the problem for logistic regression. So in logistic regression, as you know, this is exactly the cost function we had for logistic regression, this term. So the only thing, we just add this term here. It's actually the same term as the other. We just here, because in linear regression, because it's inside the parentheses. So yeah, so it's here like inside the parentheses, and here it's outside the parentheses, and don't forget to divide it by the number of examples. So we just add it also, and the gradient descent is exactly as the linear regression, but as you know, this is the sigmoid function of wx plus b, and this is the sigmoid function wx plus b, and here in linear regression is just like our hypothesis function, whatever it is, like whether it's like quadratic or even more like polynomial, like with a big dimension. So the writing of gradient descent is exactly the same. That's just the h of x are different from each other. So congratulations. Now you can start with play with machine learning algorithms. We already had some practice, enough for you like to start playing by yourself. We learned like many concepts during the course, and you can even like cite that in your resume, like when you are applying for a job or something. But this is not the end of our course, of course. This is the end of theoretical course. Next chapter is gonna be like practice chapter, like it's gonna be 100% just for practice, and it's gonna be like maybe probably the most useful chapter, because as you saw in previous practice videos, we learned like many even more concepts, and how to deal with the data, how to split the data, how to normalize the data, and we are going to learn even more. We're going to see the KNN algorithm, the nearest neighbor algorithm, the k nearest neighbors algorithm, and even like many more techniques using the TensorFlow framework, on R, of course, also. So stay tuned for next chapter, and thank you very much. See you next video.